Hello and welcome to ROHDE SCHWARZ 35 series. My name is Rainer Stuhlfahrt and I'm a technology manager wireless. And today I would like to use the opportunity to shed some light into the aspects of 5G security. So what does it mean with security in 5G? Maybe I'll come to a small analogy from the area I live in Germany. It's a beautiful countryside close to the Rhine River, the valley, and it's fully deployed with medieval castles and fortresses. And this reminds me to the historical approach when we talk about security. Yeah. So in the medieval times, the people felt secure living in a fortress castle. They had their perimeter, the walls, the moat security, and we had a drawbridge to the outside world. So this is like the analogy I'm using my network. I have a wonderful and perfectly secured firewall that blocks and protects me against any kind of outside security threats. But then we know the analogy of the Greek history. You're pretty sure all know the story of Troy, so there will always be somehow a way to bypass the kind of security anchor and the bridge. So that is the awareness we have to look into security from a very holistic view. So what are now the 5G security aspects? First, let's have a quick look into the motivation. Why should 5G be very secure? This is a valid an overview to people when we question them what should be the major concerns or what are the major concerns in the wireless networks and with connected devices. So what we see here is that security is on position number 2. Directly despite the aspect of privacy. So privacy is also a subscriber protection. Looking into the threats into the wireless network. So there are of course a couple of security threats. Started with the supply chain threat. So is the equipment that we're using somehow security proven? How can we secure the data that we keep it in a secure communication? We have the signaling connections. Of course, we have the external service, let's say the clouds, etc. Then we use the devices itself. Here this huge amount of devices, the Internet of Things. Of course, human threats is always an issue. Let's say that you can consider the fact that, let's say, your enemy is part of your community. Let's say it's the insider, typical security threat. Yeah, and also the device threat, so that device is insecure as well. In a more detailed view, I just refer here to some documents, for example, issued by the GSMA organizations with more details on aspects like device threats. So what could be possible? Of course, we all know that we can, let's say, install some malware in the devices, that we can have a bot network and use the device to build up a denial of service networks. We have, of course, the radio interface, the wireless link, so we can eavesdrop into the radio interface. We can behave as a rogue base station, for example. We can try to sniff into the signaling, the edge threats. Let's say this is the challenge in 5G when we talk about the holistic visibility. So 5G is always and everywhere, so should be ubiquitous communication. And the other part is 5G uses decentralized functions and network entities and components, which is on one side we can consider this as a security advantage because it's no longer like one centralized large control entity or one big computer that knows everything and is always under the attack. So I would call this my Fort Knox approach. Let's say all my treasuries are in one building, and then of course I use a huge well-equipped army to protect this kind of treasury. But on the other side, this gives a certain vulnerability because my enemy would know where I am and probably find some countermeasures how to attack me. So 5G is decentralized, which is then also on the other side a challenge because we may not be able to control all the entities. They are widely spread across the country. Yeah, and of course we have the core network threats and for sure like external threats which are mainly in the application part. So the entire network structure using certain functions and using this virtualized network functioning, this can be considered as an advantage, also as a disadvantage in the 5G world. Means from the motivation, 5G will become a success if we can make it somehow secure. So we see from the human persons, our customers, subscribers, they expect a high level of privacy and security. We see other type of subscribers, let's say here the industrial, or let's say the automotive is one example, with the vehicles, CV2X as one example. Therefore, of course, we have a much higher level of security in those applications. And on the other side, we see this massive machine type communication, and here the major challenge is just the widely deployed and huge amount of devices and even the different device types that we are going to use. Let's take a closer look into the security aspects. First, do me one favor, when we talk about security, we should have a holistic vision. What does that mean? On one side, in the upper part of the picture, we should look into like the organigram, like the infrastructure view. We have different components, interfaces, data servers, functions, etc. We have to ensure that they are securely communicating with each other and are securely proven. On the other side, let's have a look into the vertical view, like the protocol layers. Let's take our famous OSI model. For sure, everybody is aware with the OSI model. We have the different protocol layers. And just let's have an example. I may have the best encryption key on the physical layer, but if I install a malware on the application layer, my whole security concept is broken. Yeah? So we have to also look into security in a vertical perspective. Let's have a closer look into the wireless standards itself. Here is a generic model from 3GPP about the security. So let's start from the left side. I think these images are well known. This is since the GSM times the 2G, that we have on one side our device, so the mobile equipment officially named, and we have the subscriber identity module, the SIM card. Yeah? And both together, so SIM card plus mobile equipment, are building our known user equipment. That means we have a clear separation between the subscriber identity and also security credentials in the SIM card, and we have the mobile equipment itself. Then next step is we have the radio interface. 3GPP is that flexible that we also have, let's say, 5G, 3GPP radio access technology, but also non-3GPP radio access technology. As an example, that would be 5G in combination with wireless LAN, to give you one example. The network I'm accessing to is now considering the roaming situation, so I have a serving network which is different from the home network. So that means we have to distinguish and discuss what is the security aspects between the two networks itself. And of course, in the general view, we have a user application, let's say my client, and this accesses data from a server, so it's a simple client and server application, so the data network application. That means we have different kind of domains for security. One is the network access security aspects. So this includes encryption, ciphering, this includes authentication, and this includes also integrity check. We have a user domain security. This is the security, let's say, in the mobile equipment and the SIM card. For example, when you turn on your mobile device, then maybe you have to enter a PIN number, or you use your fingerprints or like a password that you're the correct user of this smartphone device. Some of these features are not defined by 3GPP as they can't be. Yeah? 3GPP, for example, covers the aspect of inter-operator specific, so this SBA, service-based architecture. I'm coming back with this. But on the highest level, here this red color arrow, this is the application domain security, and this of course cannot be part of the specification work. So let's have a quick look into the main security functions in 3GPP according to new radio release 15. So with 5G we introduce a kind of enhanced authentication framework. So authentication is a very big topic in wireless networks, and here 3GPP did an enhancement compared to the legacy technologies. We introduce a service-based architecture. So leveraging the communication between the network functions, that we have across the network an encrypted link that all the network entities will communicate on a secure basis only. A big topic also is in security is the communication between two network operators. For example, the case in roaming with a visitor to the home network, that we have a secure communication in between both. A much higher level of security aspect in 5G new radio is the privacy protection. So I will see that later on in details. I will never come with my real name and always use a concealed identifier. Other enhancements in 5G is, for example, the integrity and security protection of signaling and user plane. So we always have a security ciphering and also an integrity protection. And last but not least, as from the main topics, we use security in case of multi-connectivity, especially dual connectivity, private networks. In release 16, for example, we talk about a secure network slice selection and an authentication per network slice. So you see there are still some enhancements and some future evolutions. So let's also look into these detailed security. Let's say some fundamentals. When we talk about some security features, what does that mean? First, we can talk about encryption. I think that's clear. Encryption, we use the cryptography approach. We have a kind of key, and with the secret key we are encrypting the data and the signaling flow to avoid eavesdropping, that somebody else, like a man in the middle, can listen into this communication. Yeah. Then we have an authentication. So authentication verifies the identity of the certain subscriber of the certain device. In 5G we will see a module authentication, yeah, and the identity of the device and of the network, so general. And the other last part from a global perspective, so here from the IETF vision, integrity is the verification of a kind of data unit, for example a control message. Give you an example, an analogy when writing a letter. Not an email, old-fashioned person. I'm writing a letter, piece of paper, and then I will sign that letter. So with the signature on the bottom of my letter, I verify that I personally have been the origin of this kind of letter, of this communication. And this is the integrity check, so to avoid or to counter a kind of man-in-the-middle attack who could deviate the packets and behave as and download some unwanted information. We also have an integrity protection. In 5G this is new for the user data. So LTE, for example, was only on the signaling, and 5G extends this security for signaling and user data plane. So coming to a very important picture. Sorry, there are lots of acronyms. You know that game in the wireless world. So this is a kind of trust model in 5G security. So what does it mean, trust model? Regarding security credentials, we have our SIM card. Yeah? So in the SIM card we have the storage of a secret key, the master key K. This master key K has 128-bit length, or optionally even 256-bit lengths are possible as well. So this is the key that is stored securely on the SIM card, hopefully tamper-proof. The same key is because we do a symmetric authentication stored on the core network, and here this is the home network, and the important functions is this ARPF. This is the authentication credential repository, yeah, and provisioning functions. Yeah, so this ARPF processes the security keys. For example, it uses the master key K to derivate any other keys for ciphering and for integrity protection, etc. Another function, I'm starting like read it in the Arabic style from right to the left. This SIDF, this is the subscriber identity conceal and deconcealment function. So this will later on help us to release and reveal the official name of the concealed user identity. Then very important is the AUSF. This is the authentication server function. So that is the peer. In terms of security, this is my contact peer, so contact person. Whenever I try to authenticate to a network, somehow logically I will contact the authentication server function of my home network operator to verify and to go for the security entities. The communication between two networks is in a secure way, therefore we use the SEP, Secure Entity Protection Proxy Server. So this SEP is like a gateway, and it is established between two network operators and make sure that we have a secure communication. The CF, this is the security anchor function, and the CF is responsible to store security data, for example a key that is used later as an anchor key, and here important is the CF is part of the serving network. So this security anchor is, let's say, my contact person in the visited network, and for sure the CF entity will help me to guide my message request to the authentication server of the home network. And the main contact for anything is in 5G, let's say, regarding data flow and also regarding the authentication is the AMF. So it's the authentication and mobility function. So the AMF will then later on guide me to the user plane function for any kind of user plane data, and for security related it will guide the way to the serving CF function and later to the authentication server. So looking into more details, in the security flow we have different levels of security and also different kind of interfaces. So these are virtual logical interfaces. We can say the yellow box is the user plane security. So any kind of data we send over the radio interface is encrypted, and the de-encryption is performed in the G node B, in the centralized unit of the G node B. The same is for the access stratum. So the control messages for the air interface control, they are integrity protected and ciphered, and this is the responsibility of the G node B centralized unit. We also have the non-access stratum control function, and this is the endpoint between the UE and the AMF. Yeah? In addition, we have a service-based architecture, like shown here from the G node B to the user plane function, or between the network entities. So this service-based architecture guarantees that we have an encrypted link between the different network entities. Yeah? And last but not least, the orange color is the user plane application security. Please be reminded that this is not part of 3GPP. That would represent the case when we have a clear end-to-end. So for example, you use a kind of text messaging scheme and you're texting messages which are end-to-end encrypted between the message server and your user device. Yeah? But this is out of scope of the specification. So let's talk a little bit about an analogies. Sorry for the security experts, apologies. This is a simplified view of the 5G AKA, so the authentication method used in 5G. So hopefully this analogy will help you to understand. Let's take the example, I will just a visitor to another country for business trips, and I arrive at the airport at the border control. So now you see the dialogue. Yeah? The inspector, border control, and I will welcome, hello, I'm a visitor from country A. So yeah, welcome to my country B. May I ask you what's your name? Alright, my name is Mickey Mouse. You see, this is a concealed name. I'm not disclosing my real name. And then I will ask the border officer whether he's a real border control officer. Yes, I am. Here is my ID. Yeah, so the police border control officer will show his ID marker to verify that he's a real border control officer. But in response, he'll ask, do you have a passport? Now, of course, I do have a passport. Here it is. And now we see the first step in 5G. The serving network, which is in my example, this border control officer, is only doing a pre-authentication check. So he looks at the passport and does a plausibility check whether this entity looks like a real passport. But this is not yet the final verification and the final result. So now we come in 5G, the inter-network communication. That means we establish a secure tunnel, here like shown in this analogy with a VPN. I'm establishing a secure tunnel to the home network. Yeah, and on this secure tunnel, this is the responsibility of the SEP protocol entity, this protection proxy. The inspector now sends a control message to the home network and asks for verification of the passport. So the authentication is always performed and decided in the home network itself. Yeah? And also the nickname, here the concealed identity is transferred over this control message. And now in the next step, the home network will verify the authentication. So according to these secret keys, the K, the authentication result, X response, now result is the authentication is successful. And by the way, we have here now the disclosed identity. So now the home network knows that the name Mickey Mouse, the concealed ID, would correspond to my real name, Rainer Stuhlfaut. And now after authentication is successfully, the serving network will receive the official name, in our case, for example, the IMSI number. And finally, we have a successful authentication, and we can continue, and we are now attached and registered to a 5G network. To see it in more details, how these parameters look like, so the communication again, the SIM card contains, most important is the secret key K, the secret one, and this is also stored in the ARPF. Yeah. When it comes to dialog, here from the network identity, SUKI, and the deconcealment, and the home network starts calculating some derived keys. For example, based on a random number, based on the authentication message function, so AMF is a kind of hash key and a sequence number, and some non-reversible functions. They are just named F1, F2, F3, etc. They can be operator specific. Now the home network will calculate a MAC, this is a calculation result, a signed response result, a ciphering key, and an integrity key. In further advanced steps, how this looks like. So assumed the ARPF gets the identity request, or here the authentication request message. So first step is, based on the AMF sequence number, random number, the ARPF will calculate a so-called authentication vector. The authentication vector contains the MAC, the signed response, the ciphering key, integrity key, etc. And these informations are now sent to the CEAF. Remember, the CEAF is part of the serving network. So this security entity, this anchor function, receives the authentication vector from the home network, and part of this authentication vectors is stored. It's stored in the serving network. The other part is now sent over the air in the authentication response message to the device, to the user equipment. The user equipment takes those information, like the AMF, the SQN, the random number, the secret key car from the SIM card. So this calculation is done in the SIM card itself. And the UE calculates the X response, XMAC, a response, cipher key, and integrity key. The network authentication is based on this comparison. XMAC equals MAC. If these both values are calculated and attached the same, then the network is authenticated. The response, the calculation result, XRES, is sent over the air to the serving network, and here the serving network is now checking whether the express is equal to the response, and if this is successful, we have a successful authentication. Last step is the keys used for ciphering and integrity, so I key for integrity key and CK for ciphering key. These keys are calculated. A further detailed flow. So in the registration request, typically a UE registers for the 5G network for the first time. This authentication request reaches the authentication server and the ARPF. And now, please be aware, in 5G we have two possible authentication methods. One from the IETF, EARPA, aka, and another one derived from legacy LTE with some enhancements is the 5G aka. So now the ARPF, so the home network, decides which of the two authentication methods will be used. Just to see some differences, the ARPA aka is part from the IETF, so from the Internet Forum, and here the difference is that we have the generation authentication vector and the calculation of the response, and there's just one verification step. The authentication response is verified in the authentication server. Remember, this is part of the home network. The enhanced authentication procedure is the 5G aka. So here we see a slightly difference to the procedure before. So the authentication vector, no change at all, but now the authentication server will not only store the response, but will calculate a so-called hashed. A hash key, this hash function, includes the identity of the serving network name. So here to counter the fact that it could be possible that I'm going to simulate or to emulate the behavior of another network operator. Yeah, so I'm the bad guy, the man in the middle, and I pretend to be a network operator. Yeah, and I try to bypass and to deviate all the control messages to your device instead of the real network to my fake network operator. And to avoid that, now the hashed X response contains somehow the name of the network itself, so we need a trust between the two network operator. The UE calculates both a response and also the hashed response, and now we see two steps. The serving network will calculate the hashed response again and check it against the value received from the UE. So this is a first authentication step, and in the second, also the authentication server of the home network will verify the response. So we have a two-step authentication procedure. Yeah. What about the user subscriber identity? As I said, that this is also a big step in 5G security. We know our famous IMSI number, so the International Mobile Subscriber, mobile country code, mobile network code, and a subscriber identity. And now the objective is to keep this IMSI number concealed, so to not disclose it over the interface. By the way, as an alternative to the IMSI number, we can also use a so-called network address ID as a permanent user identity. And this has the name SUPI. Subscription Permanent Identity in 5G. And now this permanent identity will be concealed. It will be concealed that we only keep the mobile country code and the mobile network code. These are public information, so they will be available. Then we take this subscriber identity with a home network function, a public and private key protection scheme, and the public key is attached to the SUKey, and the private key is only, let's say, with the protection scheme ID, so that the home network operator knows which protection algorithm was used to conceal the identity. And we see it in the dialog. Here again the registration procedure. So the UE registers to a serving network, and here on the over the interface we only see the concealed ID, the SUKey. Yeah? The serve, security anchor is not aware of that, it will forward the concealed identity to the authentication server, and with the help of this subscription deconcealment function, SIDF, the home network can deconceal the identity. So the SUP is provisioned to the serving network, but only after successful authentication. Yeah. So again, my trial to behave as a network operator would fail in here. So we see the same procedure again with the identity request, just to verify that I cannot ask you for your IMSI number directly. So if with the identity request I can ask for the concealed ID or for the email number, for example. There are a lot of security keys derived out of that master key K. So I will not go in details, but just to show you here the principles. So we have various keys for ciphering and for integrity key, and also a new concept in 5G is this kind of KAMF or KCF. This is the concept of an anchor key. So the serving network calculates an anchor key from the master key procedure, derivation procedure, from the home network, and this anchor key is used for any kind of succeeding control steps. So this is also a very important one to reduce latency, and when I have a dialog, for example, or I'm in a mobility scenario that I'm doing a handover from one base station to another base station, for example, that the security procedure authentication with the home network does not need to be repeated again. Yeah? What I just mentioned at the beginning, here just one slide on this, we have a secure based interface. That means all the communication between the network entities is based on the IPsec protocol. So we have a tunneling protocol and an encryption protocol on the IP layer. And last but not least, another outlook in 5G, what we have in addition is a two-step, a secondary authentication. So that means after a successful authentication to the 5G network, we can also use a secondary PDU context-specific authentication to an external data network. Yeah? And this offers a much higher level of security also to the data network itself. Coming to my last aspects, when we now talked about security, what is still missing, and especially when they talk about some kind of testing aspects, we know we have protocol conformance testing, we do RF testing, but the simple question is, how can I guarantee that this device is working well in terms of security? So what we still somehow need is a kind of standardization process for security verification and security validation. Like my example, like a label, when you go to an electronic store and you would like to purchase another nice electric device, for example a new laptop, a new smartphone, etc., that you find a kind of label on your device that shows, yes, this device has been tested concerned security aspects. And here just an example that we are on the way to do that. For example, GSMA published some IoT security guidelines. Or an example I know from the European community, they have launched a so-called EU Cybersecurity Act. That means it's a kind of labeling, and for certain kind of functions, for certain kind of use cases, a device needs to be certified to be security. So we have 3 levels: basic, substantial, or high. For example, if I'm a car maker and would like to use a device in my car for remote controlled vehicles, then maybe it could be a requirement that I'm only allowed to use a device that is classified to be securely tested as high. Yeah? So just as one example from the 5G. That brings me to my last slide to see 5G in this very famous model by the NIST, the National Standard Institute. Yeah, so the 5G and the 5 security steps, yeah, like the name. So we can see identify. So that means in my company to have an understanding of cybersecurity. So I have the awareness. Yeah. ROHDE SCHWARZ is a cybersecurity company. The second step is the protection, so to develop any kind of safeguards and mechanism against security. For example, to install an antivirus on my PC, to have a kind of IT infrastructure. ROHDE SCHWARZ, for example, we have products like a secure web browser, like a secure network, that we have encryption interfaces, and we have a secure infrastructure that we provide. The yellow box is the detect mechanism. So here I have some measures to be able to detect any kind of security breaches. So for example, ROHDE SCHWARZ, we develop a packet inspections. We can monitor the traffic flow, and we can also monitor whether the connection is encrypted and to see any vulnerabilities here, any anomalies. The red color would be the response. That means a security attack has occurred, and now I have some kind of measures to take to respond to fight against and tackle these security breaches. And last but not least, the green color in this NIST model is the recover. So for example, my computer was crashed, and then luckily I have a backup, so I could recover that. So this kind of 5 steps model, and this is also lined into the 5G security aspects. Yeah? So ROHDE SCHWARZ is strongly committed to these security aspects. So that's from my side for today about security in 5G. Apologies for all these details I could not mention in this short time. I promise we will update our 5G technology book with more details also on security. So stay tuned on ROHDE SCHWARZ channel. Thank you very much for your time, and stay healthy.